This has been a really interesting conference, and it's a great privilege to be able to talk here, so thank you very much. I'm going to talk about some work with these people in the lower left. So here's the outline. I'm going to be talking about quantum reference frames and semiclassical gravity and beyond semiclassical gravity. I'll talk about generalized entropy and black hole thermodynamics. And I'll mostly be talking about this from the point of view of some toy models. And along the way, I have some, things to say. I didn't know exactly what to call them because I didn't want to sound too arrogant or combative, or I settled on the word ideas. But that also suggests more originality than maybe it should. But anyway. Okay, so why are we interested in quantum reference frames? Well, one of the principles of gravity is general covariance, which says we can describe physics from any coordinate system we like. The laws of physics are the same. Another principle of gravity is background independence, which says, okay, we have these coordinate systems, but there's no background structure, so we have to make those coordinate systems out of actual physical degrees of freedom. So people call these clocks and rods, but they could be scalar fields or anything you like. And then if we're doing quantum theory, then we have to be using quantum clocks and rods. And people often just don't say dynamical, and they call these things quantum reference frames, or QRFs. So I'm, in the context of this talk, not going to be really thinking about these things operationally. I'm more just going to be thinking, okay, what happens when we have a system with these kinds of degrees of freedom in them? What can we conclude about that system? And I think really the main thing that they let us do is they connect a gauge invariant description of physics with a gauge fixed description of physics. So an overall perspective neutral gauge invariant description with a description for within one set of coordinates or one perspective. And I also think they're very important in semiclassical gravity. So this is often taken to mean that the geometry is fluctuating negligibly compared to everything else. But the word geometry here is, there's a lot going on under the hood there. It really means two quite different things. So the first part of geometry is coordinate systems. We put patches on space-time. We come up with coordinates. And then there's everything else, which is sort of, we can think of it abstractly, but really at the end of the day, we have to describe it in terms of coordinates. So length, curvature, gravitational waves, and so on. Okay, so the first idea is that really it's the quantum reference frames that make semiclassical gravity interesting, and everything else is just candy on top. So those principles I mentioned, general covariance, background independence, they're really talking about coordinates. They don't really care about the particular details of the model on top of that, which is what length and curvature and so on do. And the second idea, which is really just a corollary, so if the semiclassical regime is characterized by having coordinate systems with negligible fluctuations, then in order to go beyond the semiclassical regime, we really have to let those coordinate systems fluctuate. And I would say that fluctuating coordinate systems are really the source of many and maybe even most of the interesting puzzles, foundational puzzles in quantum gravity. Okay, so the point of these ideas is to be, okay, some of them will be uncontroversial, I hope. Others will be more controversial, and maybe that will strike the balance and make for a good discussion session. So, well, we'll see. Okay, so the first toy model. I'm going to imagine I have a quantum field theory, and I have some clocks. So each of these things have Hilbert spaces, and they have Hamiltonians. And you could construct a clock however you like, but I'm just going to do the simplest possible thing, which is the Hilbert space of the clock will be wave functions of the time that it reads. And the Hamiltonian of the clock will just be the conjugate momentum to that time. And then I'm going to say, okay, obviously, the gauge group of gravity is huge, but I'm just going to look at a one-dimensional gauge group, which is time evolution. So the constraint generating that gauge transformation is the total energy. And so now we want to ask, what are the observables? So from the gauge invariant point of view, the observables of the system are just operators acting within these Hilbert spaces which commute with the constraint. So that notation means bounded operators that commute with C. And there are two kinds of these things. There are what are called dressed or relational observables, D of A, where A is some field operator. And there are also reorientations, which are changing the time read by the clock without acting on the fields. And you can show that these completely generate this gauge invariant algebra. And one thing you can notice is that this dressing is just a unitary map. It's just a conjugation of the field operator by some unitary operator, which means that the map between the field operator and the dressed operator is an algebraic isomorphism. And so this is a connection between the gauge invariant description, these gauge invariant operators, and the gauge fixed description, which is just this bare A, which you can think of as the operator you're acting with in the gauge fixed setting where the clock time is fixed to a certain value. Okay, so this is an isomorphism, but the third idea is that this map between gauge invariant things and gauge fixed things is not generally an algebraic isomorphism. So there's a very simple thing we can do to demonstrate that. We can just say, okay, so previously this clock, it had its energy spectrum was unbounded. It was the whole real line. But suppose you restrict the energy spectrum of the clock to some proper subset of the real line. So this is, you might say, this is a more realistic model, especially if you want to impose a lower energy bound. Well, if you do this, you find that if you compose two of these dressed operators, it's not the same as dressing the composition of the bare operators. You have to take into account the fact that the clock has a restricted energy spectrum, so that when you impose the constraint, the fields will also have a restricted energy spectrum. So you put in this projection operator. And so at the gauge fixed level, you don't have an algebraic isomorphism. You really have a deformation of the gauge fixed algebraic relations. And this is a very simple deformation, but more interesting models have more structure. Okay, the fourth idea is that if you have a quantum clock, then that's going to regulate UV divergences in fields. So any first course on quantum field theory, you learn that when you try to compute correlators of fields, so 2-point functions, 3-point functions, and so on, and you take the points at which you act with these fields and you take them close together, then these correlators typically diverge in that limit. And that's because of the UV divergences in the theory. But the gauge invariant observables, the actual gauge invariant observables are these dressed operators. And these dressed operators are, by definition, they depend on the time of the clock. And in a normalizable state, the time of the clock has to be smeared. It can't be arbitrarily, it can't be localized like a delta function because you get an unnormalizable state. And this smearing suffices to regulate these UV divergences. So that's very interesting. As soon as you have a quantum clock, you get rid of UV divergences in fields. And there's recent work which has shown that this works for entanglement entropies as well. So by these people, and if you want our perspective on it, we wrote these papers which talks about it more from a QRF point of view. So I can describe how that works. So before I wrote down the algebra of all of the observables of the fields in the clock, but you could equally well say, let's restrict to some subregion. And suppose I'm only allowed to act with field operators in that subregion, and I still have access to the clock. then the algebra that you would write down is you take the field operators in the subregion, you tensor it with what you can act on the clock with, and then you impose gauge invariance by restricting to things which commute with the constraint. Now it turns out this kind of algebra has been well studied 40 years ago by mathematicians, and it's called a cross product. So you take the QFT algebra, you have some action of this group R of time evolution on that algebra, and you construct this algebra in this way. Now it's well known that if you're in the vacuum state of the QFT and you go to some subregion, the fields will be thermal in that subregion because of entanglement between the subregion and its complement. So if you're in a Rindler wedge, the fields will be in a thermal state with respect to a boost, and that leads to the Unruh effect. So let's say we just choose a clock which measures the time corresponding to that thermality. So in the Rindler wedge, we would pick a clock which measures time along a boost. Well, then what happens is fascinating. It's the same as with the correlators. The entropy of this just the algebra of the fields itself is UV divergent. That's because there's an infinite amount of entanglement arbitrarily close to the boundary of this region. You might have heard that QFT algebras are type 3. But it turns out that once you compute the entropy of this algebra with the fields and the clock, and you impose gauge invariance, then the entropy is, in fact, UV finite. So you might have heard this is a type 2 algebra. So I'm writing these entropies as functions of the algebra. Really, they depend on a state as well. So whenever you compute an entropy, there's some state and there's some subsystem that you're looking at. And the algebra defines the subsystem, and I've left the dependence on the state implicit here. Okay, so the fifth idea is that within a semiclassical regime, this slightly, well, depending on your perspective, you might think it's a convoluted construction of some entropy, which happens to be UV finite. But semiclassically, this is actually much more relevant than that suggests. It's actually the same as the generalized entropy of the subregion. So what do I mean by semiclassically here? So I have the clock, I have the fields, and like I said at the beginning, for me, semiclassically really is talking about having coordinates with small fluctuations. So I want the time of the clock to have a small variance within whatever state I'm considering. Alternatively, you can say that the energy of the clock has large fluctuations. And more precisely, you have to state this in terms of a hierarchy to have some unitless statements. So what you want is the fluctuations of the energy of the clock to be much larger than the fluctuations of the energy of the fields. And if you do this, you can compute this entropy, and what you find is some leading order terms. So there's a constant, which is essentially just a normalization. There's the energy of the clock. And there's also a relative entropy of the fields with respect to the vacuum. And now if you introduce some UV regulator so that you can split up the relative entropy into a term corresponding to the actual entanglement entropy of the fields, and you use Einstein's equations, keeping in mind that the clock itself has some energy momentum, it turns out that you can just write this thing, these leading order terms, as the area of the boundary of the region divided by 4gn, plus the entropy of the fields, plus some subleading corrections, which is the generalized entropy. So this was a toy model, but it's actually closer to perturbative quantum gravity than you might think. So one example of where this applies is if you take a Killing horizon, and you take some boost of that horizon, so maybe this is a horizon of a black hole, and you take some cut of the horizon, then the fields outside of that cut will be thermal with respect to a boost around that cut. And the constraint that generates this boost, it comes from Einstein's equations. More specifically, it comes from the Raychaudhuri equation. And if you write this thing down, you have a term which is the integral of the stress tensor over the horizon with some multiplied by a coordinate v, a null coordinate along the horizon. And you also have a boundary term, which is the area of the horizon in the asymptotic future. And really, you can recognize the K boost, the generator of the boost in the fields, as the energy of the fields in this model, and the area term is the energy of the clock. And so this semi-classical regime that I mentioned, the fluctuations of the clock energy are much larger than the fluctuations of the field energy. If we write it in these terms, what we see is that it means that the fluctuations of the area in Planck units are much larger than the fluctuations of the field boost energy. So the fact that this is in Planck units means that the geometry isn't actually fluctuating that much. It's just fluctuating a lot in Planck units. Okay, so the second toy model is to do with the generalized second law. So along this horizon, we can pick any cut we like. We can construct this crust algebra using the area of the horizon as a clock for the boosts. And you can do this for two different cuts, one to the future of the other. And what you find, or what these people showed, is that in a semi-classical regime, the entropy associated with the algebra outside of the later cut is at leading order greater than the entropy associated with the earlier cut. And because these are the generalized entropies, this is just the generalized second law. So the second law of thermodynamics in the presence of black holes. Okay, this is semi-classical gravity, but I want to go beyond the semi-classical regime. And okay, why would we want to go beyond the semi-classical regime? Beyond just it's a very nice to be able to have done it. Well, one reason is that this semi-classical regime is not stable. So you can very easily come up with situations in which you start off in a semi-classical regime, but you evolve into a situation where you don't have the semi-classical regime anymore. So note that this area at future infinity, this is fixed in time, but the boost energy of the fields evolves. So as you pick a cut that goes up the horizon, this boost energy will evolve. So you can imagine you start off in a state in which this semi-classical regime is obeyed. And now outside of the horizon, I'm going to set up two clumps of matter. I'll put them in a highly entangled state across boosts eigenvalues, so that the overall boost the overall boost of this two clumps of matter has small fluctuations, but the individual clumps of matter have large boost fluctuations. And then you let one of the clumps of matter fall in. Because of this entanglement, what you now find is that the boost fluctuations along the horizon has now become much larger, so you can leave this semi-classical regime. And then you can let the second clump of matter fall in, and the entanglement is purified, and you return to the semi-classical regime. But okay, so the ordinary generalized second law doesn't seem to be able to describe this kind of process because it requires you to make this semi-classical assumption. Okay, so how can we go beyond that? Well, in quantum information, these kinds of entropy inequalities typically come from having subalgebra structures. So you have one algebra that's a subalgebra of another, then you can apply just standard quantum information inequalities to those algebras. But here it's kind of weird. The algebras that were constructed like this, they're not subalgebras of one another. So the algebra of the later region is not a subalgebra of the earlier region, which is kind of physically unsatisfying. You would expect to be able to do anything you could do in the smaller region, you would expect to be able to do in the larger region. But this is sort of saying that's not true. But we've been missing some ingredients. The reason this happened is because these algebras were constructed by imposing boost invariance, but the boosts of these two regions are different. So obviously, an operator invariant under one boost doesn't have to be invariant under another boost, so that's what ruins having a subalgebra. The solution is obvious. We just have to impose invariance under both of the boosts. In gravity, we have to impose invariance under everything, so obviously this will be something we have to do along the way. So now we have two constraints, C1 and C2. But now we have another issue, which is that the difference of two boosts is a null translation along this horizon. And such a null translation is going to move the fields relative to these cuts, or it will move the cuts depending on the way you look at it. So having fixed cuts and fixed exterior regions is no longer compatible with gauge symmetry, which leads to idea 6, which is that these exterior regions outside of cuts have to be defined relative to quantum reference frames. So in contrast to the boost clock, which was a quantum reference frame inside of the region, now we have to introduce some quantum reference frames which actually tell us where the region is. And I call these dynamical cuts. So an example of this is, you could say, suppose I have some particles which are falling across the horizon, and I just say at the point at which they cross the horizon, that's my cut. Now, the particles are subject to diffeomorphisms. They move around. So when you do a diffeomorphism, you'll move the cuts. And so this will give rise to well-defined physical subsystems, unlike previously for the fixed cuts. And of course, this is just one example. There are many other ways you could construct these dynamical cuts. But in this paper, I discussed a toy model. So I just imagine I have some number of these degrees of freedom, which I use as dynamical cuts, labeled by A. Each of them I give this L2 of R Hilbert space, consisting of wave functions of the location of the cut on the horizon. And there's no time to do technical details, but once you have this degree of freedom, you can construct these algebras which correspond to these subregions outside of these dynamical cuts. And the point is, now that you've done this, you do have subalgebra structure. So if you condition on one cut being located to the future of another cut, then the algebras of the two cuts obey this subalgebra relationship. And you can use quantum information to deduce this inequality. And these entropies are really generalized entropies. So this is almost the usual generalized second law, except there's an extra term on the right-hand side, which you can, roughly speaking, think of as the free energy of these degrees of freedom that we use to define the cuts. So idea 7, the generalized second law has to account for the heat of quantum clocks. So that's what free energy is in the second law. It accounts for heat. And so yeah, that's idea 7. And idea 8 follows on from that, is that quantum reference frames have the potential to shed some light on black hole information. And one way in which that can happen, well, this free energy, it can actually be arbitrarily negative. And what that means is that the generalized entropy can decrease, because if the free energy of the cuts becomes small, then we don't need the later generalized entropy to be larger than the earlier generalized entropy. It can curve back down. And that might lead you to suspect maybe this can do something like a page curve. I have no concrete calculations to support this. It's just a loophole. And a sort of a speculative thing you might say is that, okay, at late times, maybe the quantum reference frame you're using becomes entangled with some large number of Hawking particles or whatever. So the free energy is the energy of the cuts minus its entropy. So if the cuts become very entangled, then the entropy becomes very large and the free energy becomes very negative. Okay, so idea 9 is that, okay, this is based on ongoing work with Laurent Fredel, and we hope to have it done in the next month or so. It's based on the idea that the gravitational field itself provides natural quantum reference frames. So in these toy models, the QRFs I've been using, they're sort of extra things I add. They're auxiliary clocks or dynamical cuts. But ultimately, we would want to form these things out of things which actually exist. So the gravitational fields say clocks can exist. I'm not saying they can't exist. But, okay, so an example of this is on a null surface. So on a null surface, there's a natural decomposition of the fields. There are a couple of papers by Chambelli, Fredel, and Lee which describe this nicely. So you have a decomposition into the area element of the null surface and its canonically conjugate partner, which is called mu. And you also have all the radiative degrees of freedom, so the matter and the gravitational waves and so on. And omega and mu are really what are responsible for the usual notions of time, null time that we use on the null surface. So for example, affine time is defined to satisfy this equation if you look at the definitions of these fields. So once you quantize these fields, they give you a quantum reference frame for null times. So before I was looking at one-dimensional groups of boosts or two-dimensional groups of boosts and translations, but really these would be a quantum reference frame for a much larger group, which is the complete group of orientation-preserving reparameterizations of the null coordinate. And the constraint generating this thing is the Raychaudhuri equation. Okay, so idea 10 is that quantum reference frames made from fields are not well understood. And I just highlight two aspects of that. The first is that when we quantize fields, we have to, well, usually we pick a vacuum, which is annihilated by negative or positive frequency modes, depending on your convention. But this isn't a diffeomorphism invariant notion. So when you do diffeomorphisms, you change what it means to be positive or negative frequency, and this is what is responsible for things like the Hawking and Unruh effects. And also, you have to normal order the fields in the constraints, so in the stress tensor, for example, and this can lead to anomalies. So for example, in this case of null reparameterizations, you have to consider a Virasoro algebra instead of this diff plus R. So I don't know yet, we're working on it, I don't know yet how to make a QRF out of a field and take these things into account, but there's very quickly a third toy model, which is what I call a QFT-like QRF. So I'm going to imagine that we're dealing with a situation with the gauge group of translations in 2 dimensions, so R squared, and there's some system with this Hilbert space HS with the corresponding generators of gauge transformations P0 and P1. And I'm going to attach to that some frame, which will be a one-dimensional harmonic oscillator. So the harmonic oscillator has a position and a momentum, and these two things do not commute, so they don't give you a unitary representation of the gauge group, but they give you a projective representation of the gauge group, which is, okay, this is an anomaly in the representation. So that's similar to the QFT. And then you can use these phase space variables to dress the position in 2D space from this 2D translation group. And you can write down some gauge constraints in this way. Okay, so now you want to ask, okay, this is a model. What are the, first I just want to say there's a preferred vacuum for the frame. It's annihilated by the annihilation operator. So this, again, is like the QFT. You have positive, negative frequency modes and so on. So what are the observables? So we take the algebra of bounded operators acting on these things. We restrict to operators which commute with the constraints. And what you can show is that this algebra is made up of dressed observables again. And for each operator acting on the system, you have a corresponding dressed operator that's a gauge invariant thing. And this is a one-to-one it's a one-to-one map between the gauge invariant things and the gauge fixed things. But going back to the idea that I mentioned before, this is not an isomorphism. This is a deformation. And it's got some complicated, there's some complicated formulas that you can write down which give you this deformation. So if I compose 2 of these dressed operators, that's not the same as composing the 2 individual Baire operators with the ordinary algebraic composition. You have to use this star product. So this is complicated, but there's lots of structure here, and importantly, there are physical consequences. So I'm interested in entropies, and when you have a deformed product, you deform entropies. So The exponential of an operator, this is changed because you have to use the star product. The logarithm of an operator is changed because that's the inverse of the exponential. And so the von Neumann entropy is changed. Now this is, you can imagine it would be a very complicated calculation to use this deformed product and try to compute this thing for some state. But if you go to a semiclassical regime, things simplify. So a semiclassical regime, in this case, corresponds to having the first few terms in this series be a good approximation to the product. So we can truncate to the first two terms and then compute the entropy, and there's a way you can do this, and you get some extra term which corresponds in some way to the energy of the frame. And okay, so this is a toy model, but this work in progress, using the area element and its canonical partner as a quantum reference frame, you actually get very similar structure. And this energy of the frame term seems to correspond to something like an area term. Okay, so to wrap up, these are my 10 ideas. I'm glad I didn't call them 10 commandments, but hopefully that will help with the discussion. Thank you very much.